So with those introductions, we'll begin today's presentation and we can move to slide 2 of the presentation. So as I said, we would introduce ourselves, the presenters of today's presentation. I have already done so as the moderator of the session, and I'm joined by my two project officers in my team who are leading the licensing components of the NPD and the NSDF projects. They are Dr. Matt Herod, Project Officer and Licensing Lead for the Nuclear Power Demonstration Closure Project, and Mohammed Sharif Gassem, Project Officer for the Near Surface Disposal Facility Project, both, as I said, within my team, the Canadian Nuclear Laboratories Regulatory Program Division. So this slide shows the key messages of today's presentation, and it's the points that we hope you take away from once the webinar is finished. First, CNSC is a performance and science-based regulator that adopts a risk-informed approach. In addition, the suitability of waste for disposal in a particular facility must be demonstrated by the safety case and supporting safety assessments. Waste classification is the categorization of different types of waste and plays a key role in managing all waste streams, including those from operational, decommissioning, and environmental remediation activities. Waste characterization determines the properties of waste and helps in determining how to best manage waste. So as I indicated in my introductory remarks, the purpose of today's webinar is to provide a general overview, hoping to reach as broadly as possible in our participants, giving you that knowledge on explaining what radioactive waste is, how is it classified and characterized in Canada. And we encourage you to ask your questions using the question and answer function in Zoom. So as I also indicated earlier, but now you can see it on a slide, this slide is just meant to situate us all in terms of where we are in the webinar series that we've been hosting with respect to these projects. So today's session is the third CNSC-led webinar with topics tailored around the near surface disposal facility and in situ decommissioning projects, which herein I'll refer to as ISD. Today's session is not going to revisit previous topics covered. If you are not aware of or unable to attend previous webinars, we'd be more than happy to send you a copy of the presentations that we delivered as part of those webinars, should you be interested in receiving those. This series of webinars is designed to present general information on the topics listed, and then followed by a question and answer session where we can answer questions on this topic specific to the NSDF and ISD projects that you may have on the specific topic covered of today. Registration is now open for all of the upcoming webinars listed, and we encourage you all to sign up for the ones that you are interested in. And we'll circle back to this slide a little later in the presentation slide, where we'll actually provide you the information on each webinar and how to register. So as part of the first topic that we'll be covering today, we'll begin with project updates on the NSDF and ISD projects. For this, I'll turn the presentation over to Mohammed, Project Officer and Licensing Lead for the NSDF project.
Thank you, Candida. Good afternoon and welcome, everyone. So my name, as stated before, is Mohammed Sharif Gassem. I'm the Project Officer with the CNSC, as mentioned, and I'm the lead licensing lead for the NSDF. So first is the update on the NSDF project. CNL submitted an updated application for the Chalk River Laboratories license amendment to construct the NSDF to the CNSC Secretariat on March 26, 2021. The application has been updated to reflect the NSDF being constructed outside of the existing waste management area facility authorization, FA, and included recent project documentation. There are no new updates to provide for the MPD or WR1 projects since our recent webinars on these projects. As mentioned, we can send you a copy of the presentations from those webinars should you be interested. Alternatively, project updates can also be found in the recent features like articles that have been posted on the CNSC website. Now I turn the presentation over to Dr. Matt Herod, Project Officer a licensing lead for the nuclear power demonstration closure project.
Thanks, Mohammed. Welcome everyone. So I'm Matt Harrod, and I'm the licensing lead of the NPD closure project. So we'll now talk and transition to the key topics of this webinar, the classification and characterization of radioactive waste. So to begin, what is radioactive waste? So radioactive waste is any material, solid, liquid, or gas, that contains a radioactive nuclear substance as defined in Section 2 of the Nuclear Safety and Control Act, and which the owner has deemed to be waste, and for which there is no foreseeable use. The radioactive waste produced in Canada is managed safely in specially designed facilities that the CNSC regulates and licenses. Licensed activities produce many different types of waste, such as uranium mine and mill tailings, medical isotope waste, spent nuclear fuel, as well as materials contaminated with low levels of radioactive substances. In addition to nuclear substances, radioactive waste may also contain non-radioactive hazardous substances, often called mixed waste, thus making it more critical that the waste is managed with the health and safety of Canadians and workers and the environment foremost. Since all nuclear substances associated with licensed nuclear activities will eventually become waste, the safe management of that waste is integral during the licensing review process for every licensed facility and activity. So the maps on these slides give an overview of the various waste facilities located around Canada. The map on the left shows radioactive waste management sites in Canada other than spent fuel storage locations. On this map, the orange dots represent active or inactive decommissioned uranium mines, which are located in Saskatchewan, Ontario, and the Northwest Territories. These sites have waste from uranium mine processes as either waste rock or mine and mill tailings. The other symbols represent waste sites where nuclear activities have produced radioactive waste. The different symbols represent the different classes of waste at these facilities. For example, at Chalk River Laboratories, low and intermediate level radioactive waste are all currently in safe storage there. The map on the right shows spent fuel storage locations. From that map, we can also see that there's also spent fuel at the Chalk River Laboratories site. So now we'll get into waste classification. And the term waste categorization predates waste classification, and these terms are often used synonymously. Over time, a number of schemes have evolved for categorizing radioactive waste according to its physical, chemical, radiological, and in some instances, biological properties. Radioactive waste is classified differently from one country to another, but today we're going to only talk about Canada. The waste classification system is generally delineated according to the degree of containment and isolation required to ensure safety, with consideration given to the hazard potential of different types of waste and the time frame associated with that hazard. The Canadian Standards Association, CSA, in collaboration with industry, government, and the CNSC, has developed a standard, CSA N292.0, that recognizes 4 main classes of radioactive waste. These are also reflected in CNSC's regulatory document 2.11.1, Volume 1, Management of Radioactive Waste. The purpose of waste classification is to assist in devising strategies for waste management, planning, designing, licensing, and operating waste management facilities, identifying the hazards associated with the waste, determining the type and degree of radiological protection required for a specific waste and choosing the appropriate management process, and facilitating communication between waste generators, regulators, and other stakeholders by providing a common framework. The main requirements for defining waste classes is that the classification system shall be based on the 4 general classes of waste and shall consider the site-specific safety case and supporting safety assessment required for the waste management facility or activity and the time frame associated with the hazard potential of the waste. So now we'll get into the classes in a little more detail. So first, low-level waste. Low-level radioactive waste contains material that is more radioactive than established unconditional clearance levels and exemption quantities allow, which are set out in the Nuclear Substances and Radiation Devices regulations. The class of waste typically has limited amounts of long-lived radionuclides, requires isolation and containment for up to a few hundred years, and may be disposed of in near-surface facilities. Low-level waste does not typically require shielding during handling and interim storage. Shielding refers to a barrier between the waste and nuclear workers to stop or reduce ionizing radiation and the doses resulting from that exposure to ionizing radiation. As an example, low-level radioactive waste includes contaminated equipment from the operation of nuclear power plants, like protective shoe covers, clothing, rags, mops, equipment, and tools. So intermediate level waste contains long-lived radionuclides in concentrations that require isolation and containment for periods beyond several hundred years. Due to its long-lived radionuclides, intermediate level waste generally requires a higher level of containment and isolation than that which can be provided in near-surface repositories. It typically requires shielding during handling and interim storage, and this type of waste includes reactor refurbishment waste, ion exchange resins, and some radioactive sources used in radiation therapy. No precise boundary between low-level radioactive waste and intermediate-level waste can be stipulated. In order to appropriately classify waste as either low-level or intermediate level, a full understanding of the waste must be obtained, including the waste generation process, identity of the radionuclides present, their concentrations and properties. In addition, the handling requirements, i.e. shielding, and time frame needed to safely isolate and contain the waste in a storage or disposal facility must be determined. In practice, the classification of most waste is relatively clear based on these factors. Where things get complicated, though, is with legacy and decommissioning waste, where the waste is heterogeneous, that is to say, composed of many different types. Some of the information is lost, or waste that is produced in an unusual manner that makes characterization difficult and contains hard to detect radionuclides. I'll now turn the presentation over to Mohammed.
Thanks, Matt. Now we move to the high-level waste. So high-level radioactive waste is used nuclear fuel that has been declared as radioactive waste and or is waste that generate significant heat via radioactive decay. High-level waste is associated with the penetrating radiation and thus shielding is required. High-level waste also contains significant quantities of long-lived radionuclides necessitating long-term isolation. Placement in deep, stable geological formation is recommended for high-level radioactive waste. Note that while reprocessing of used nuclear fuel was done in the past at Chalk River site for testing purposes, it's not a current practice in Canada. Next slide. The uranium mine and mill tailings are a specific type of radioactive waste generated during the mining and milling of uranium ore and the production of uranium concentrate. Many countries do not consider uranium mine tailings as a separate class of waste. In addition to tailings, mining activities typically result in the production of large quantities of waste rock during excavations to access the ore body. The waste contain long-lived radionuclides that do not decrease significantly over extended time periods. Tailings and waste rock must be managed over the long term because they could contain significant concentrations of radioactive elements, primarily thorium-230 and radium-226, along with the associated decay products. Tailings are the waste produced by grinding the ore and the chemical concentration of uranium. When dried, tailings have the consistency of fine sand. Waste rock is simply rock material removed from the mine to gain access to the ore. It has low concentration of uranium. Waste rock is separated into clean rock or mineralized rock according to its mineral content. Tailings and mineralized waste rock are contained in engineered surface and near surface waste management facilities located near the mines and mills. Next slide. we will now transition from discussing waste classification to waste characterization. The CNSC requires that licensees perform waste characterization at appropriate steps in the management of radioactive waste. Waste should be characterized at the point of generation, but characterization may be conducted at any time during the management of waste. Proper characterization of waste underpins all aspects of radioactive waste management and enables classification of waste and the handling and safety requirements for the waste all the way to the disposal of the waste. Waste characterization is a thorough analysis of what is contained in the waste, radionuclides relevant to safety, as well as all the various radiological, mechanical, physical, chemical, and biological attributes of waste. Many methods may be used to characterize waste depending on its source, type, for example, soil or cement, and the radionuclides expected to be present. As a result, waste characterization can be extremely complex. The purpose of characterization should be central and also take advantage of all existing information on the waste, such as process knowledge. The purpose of waste characterization is to assist with the safety assessment of facility or activity, define segregation and safe handling requirements, define container type, packaging materials, and packaging methods requirements, determining condition, processing or disposition options, and verifying the suitability of the intended disposition path. Now we target the waste characterization roles and responsibilities. So the role of the licensee in waste characterization is to perform applicable and required characterization activities to all stages of the radioactive waste cycle, including generation, handling, processing, transportation, storage, and long-term management. It is the licensee's responsibility to conduct waste activities in accordance with regulatory requirements. Licensees are also required to maintain all relevant records from waste characterization activities. The role of the CNNC in waste characterization is to thoroughly review the licensee's waste management processes, including characterization. CNSC inspectors perform regular inspections and technical reviews on all types of facilities and activities in Canada that generate or manage waste. Now I will turn the presentation over to Matt.
Thanks, Mohammed. So this slide gets a little technical, but the information is very important to show how licensees characterize waste and what the CNSC is actually reviewing when we examine licensee characterization programs and results. There are many methods of characterizing waste, and Annex B of CSA N292 goes into more detail on the available methods, and a new standard, CSA N292.8, characterization of radioactive waste and irradiated fuel, is currently in development. Characterization at a high level is goal-oriented. The goal is to sufficiently characterize the waste to inform classification, handling, packaging, disposition, etc. To do this, licensees often use the data quality objective process, which provides a well-organized approach for planning and implementing waste characterization activities. The process serves to define the problem, identify the decisions to be made, and specify the quality requirements for those decisions and the measurement data in support of developing a waste characterization plan. This process is complemented by the data quality assessment, which is a statistical evaluation to determine if data are of the right type, quality, and quantity to support waste characterization plan objectives. The data quality assessment process is used to evaluate the results against the objectives of the characterization plan to inform decision-making. The method for waste characterization used in a practical sense can be divided into three types: inference, non-destructive analysis, and destructive analysis. Inference methods use process knowledge about the source of the waste and its production to understand what radionuclides are likely present. Process knowledge is critical for all types of waste characterization methods, however, and is not exclusive to inference. These are complemented by the use of scaling factors or modeling. Scaling factors, when properly determined, allow the determination of difficult to measure radionuclides through a surrogate isotope that is easy to measure through their shared source. A good analogy would knowing that there are beavers around when you see chewed trees, even though it would be difficult to directly count the beavers. Modeling allows the determination of radionuclides in a sample through computer analysis of the radiation environment the material has been exposed to, for how long, and its composition. Non-destructive methods allow the determination of radionuclides in a sample through gamma spectrometry, which in some cases allows the sample to be reused afterwards, as it only detects gamma radiation emitted from the sample and does not need to destroy it to do so. There are also other methods commonly used in many industries to analyze the general elemental composition of a material without destructive lab analysis, such as X-ray fluorescence. Can everyone hear me? I just got a note. Yeah, okay. Destructive methods of analysis must process the sample in some way for it to be analyzed. For example, dissolution of the sample to prepare it for mass spectrometry analysis. There are many, many types of destructive analysis that can be used depending on what the characterization objectives are. Usually some type of lab mass spectrometry is one of the most common ones, or alpha spectrometry, for example. Waste characterization is a key aspect of assessing the long-term safety of disposal facilities for radioactive waste. The information provided by the waste characterization forms one of the most important inputs into the models used to demonstrate long-term safety. Therefore, quality data on the waste is required. CNSC RegDoc 2111 Volume 3, Safety Case for the Disposal of Radioactive Waste, requires that the safety case must include the waste information and waste acceptance criteria of a disposal facility. The safety assessment must incorporate the disposal system description, and this includes the waste characteristics. In addition, the identification of key radionuclides or principal radionuclides or dominant radionuclides, this term is frequently interchangeable with those other ones, is done through the safety assessment. Usually these are radioisotopes which are the most mobile in the environment or give rise to doses to receptors when long-term modeling is performed. This enables limitations to be placed on the amount of these key radionuclides through the waste acceptance criteria and informs the waste characterization process. The waste acceptance criteria, developed through the long-term safety assessment and other inputs as well, requires that all waste that will be stored or disposed of in a facility meet this criteria. Because the WAC is developed using the long-term safety assessment, compliance within these limits ensures that the facility will meet acceptance criteria over its lifetime. In addition, in order to ensure the waste meets the WAC, it must be adequately characterized. As a result, waste characterization is an essential part of long-term safety. So CNSC's evaluation of waste characterization takes a number of different paths. And through our risk-informed regulatory oversight of licensed facilities and activities, CNSC staff and inspectors perform a number of verification activities, such as physical tours and walkdowns of different nuclear facilities, compliance inspections, desktop reviews, event reviews, and trending and operating experience and lessons learned reviews. So now I'll discuss the waste that's actually found at the nuclear power demonstration facility. So the waste at NPD is classified as low and intermediate level. The low-level waste component is the moderator system, but it is primarily composed of contaminated piping, contaminated asbestos pipe cladding, building materials, etc. The intermediate level waste component is primarily composed of the reactor vault components at NPD. These include the zircaloy pressure tubes, the stainless steel end fittings, the calandria, and other components exposed to neutrons when the reactor was in operation. The primary heat transport system is also considered ILW due to the contamination within that system. To characterize this waste, CNL, the proponent, used a combination of sampling and inference methods, specifically neutron activation modeling. All used nuclear fuel was removed from NPD in 1987 and is now safely stored at the Chalk River Laboratory site. I'll now turn the presentation over to Mohammed.
Thanks, Matt. Now, talk about WR1 reactive project waste. So the waste at WR1 is also classified as low and intermediate level. Similar to MPD, most radioactive waste in the WR building is situated in the reactor vessel, including the calandria and fuel channels, as well as asbestos and coolant remaining in some reactor components. The fuel was removed from WR1 in 1985 or 86 and is stored in specially built the concrete canisters in the White Shell Laboratories waste management area. Now I'll talk about waste proposed to be stored in the NSDF or disposed at the NSDF. Should the near surface disposal facility be granted approval by the CNSC Commission, it would be licensed to only accept low-level waste. The type of waste streams the NSDF designed for include type 1, which is waste including contaminated soil and other waste materials with characters similar to soil that can be placed in the mound with what would be required for disposal of soil. Type 1 waste is generally generated by environmental remediation and contaminated lands. Type 2 waste is a mixture of radioactive waste, debris, refuse, soil, and soil-like waste, and includes waste that are anticipated to be at least 50% soil or soil-like in nature. It also includes varying amounts of refuse containing organic and compressible materials that are impractical to separate from the soil or soil-like material. It is generated by CIL environmental remediation projects at the Characterization laboratory site. Type 3 waste is not like waste, soil waste, that includes materials that can be excavated and handled as bulk materials, but do not have the physical characteristics of soil and soil-like materials. Type 3 includes process waste, highly organic waste, highly compressible wastes, and flowing waste. The waste that do not pass the slump test, and similar waste types. Type 4 waste is decommissioning and demolition waste that includes typical materials used in construction, such as concrete, asphalt, brick, lumber, circular steel, process equipment, piping, wood, and other building materials produced by decommissioning and demolition activities. Type 5 waste is package waste containing rigid packages, which include drums and waste boxes, galvanized stainless steel or carbon steel, and other waste containers. Type 6 is oversized debris that includes waste that does not fall within the definition of waste types 1 through 5, primarily because of its size or shape. I will turn the presentation back to Candida.
Thank you, Mohammed. So that brings us to the end of our presentation. And as I indicated earlier, sorry, hold on. There's just some echo. So as I indicated earlier, we were going to end off with our with a slide on the upcoming webinar series that we have. We've got one on May 20th is going to be focused on how we carry out compliance verification, how CNSC staff does so on licensed facilities and activities. And we've also got a general overview of the format and structure of CNSC staff documents that we present to inform our commission and to inform their decision making. What does the format and the structure of our environmental assessment reports and our licensing commission member documents look like, and how do we document our technical assessment and findings in those documents? And again, these are going to be a general overview, but we'll be available to answer questions specific to how those topics relate to the NSDF and the ISD project. So we told you that we would provide you the information on how to register. So we have provided that link for you on this slide. It's also available on our main webpage. It may not always be easy to navigate, so that's why we've included it on this slide for ease of reference. And we really hope to see you all there in future sessions. So with that, that concludes the presentation.